Pranati, are you there?
Yes, sir.
Where are others? No one has joined. I'm waiting.
So we were having project review till now, so maybe that's why they're taking time. Like few
Should I
people
wait
were
or we
having
will
project,
continue?
so you can start.
Okay.
So they'll join as it's going on.
All right. You communicate in your group, okay, personal group, and tell them. Yeah.
Yes.
Because we have to bind up for 2 hours in that way. I will be late. Good afternoon, all. So, this is my treatment engineering, all the unit operation and the various water characteristics, as well as we are moving for now for the water distribution network. Today I will be discussing discussing about the wastewater engineering, mainly sewage treatment plant unit operation, as well as the designing planning of sewer network. So that is the main part that we are going to discuss. In the last class, we were here ozonation and disinfection we were discussing. So I'm coming for the water distribution network. How to design a water distribution network. Once the water is treated and is stored in a clear water reservoir, you have to distribute this water for the community. And then distribution, while you're drawing a water distribution network, while you're designing a water distribution network, two things you have to be taken care in respect of like the design period and in respect of the surface service point of view. One is the losses should be minimized. The losses, maybe all the losses including head losses, commercial losses, real losses, apparent losses, altogether should not cross 10 to 15%. Maximum 15% losses are acceptable in the distribution pipe network. Quality of water you have to maintain is another thing. Third thing is the water should be uniformly distributed throughout the whole community. Suppose we have Bangalore city, we're having various zones and wards. In all the wards, how much is the coverage? Suppose that we have 80% water coverage. So water should be uniformly distributed throughout the whole city and till the end consumer. Suppose in a one line, we in a one zone, the last consumer end, with the last connection you have given, there also the same pressure and with the uniform quantity of water should be should be supplied till the last consumer end. It's not like this. Water supply should not be non-uniform. And our objective is it depend how you have designed the water supply and treatment part. Suppose somewhere we have a 24 hours water supply. It's our goal actually, 24 hours water supply. And in India, uh, 99% we don't have 24 hours water supply except few cities. Wherever you open the tap and municipal water, treated water should come to your house, right? It's not like this, but we have it's a target, like we should have a 24 hours water supply to your every household. That is the things that you have to take care. And the quality aspect of water, you should not compromise with the quality. The treated effluent, the treated water sample you have to take daily basis. and you have to check all the parameters, physical, chemical, and biological parameters. Testing laboratory will be there. You have to check their pH, turbidity, taste in order, color, their beauty, and as well as the pathogenic pathogens also, micro MPN test, you have to do that. So the water should be clear, and whatever the objective we have defined earlier for the drinking and potable water, these objectives should fulfill. And then you have to take the raw water sample also, and you have to take a clear water sample, and the efficiency of the treatment plant also, you have to check it. Okay. So this is water distribution network. Will take 15-20 minutes max for the water distribution network. Then we'll move for the wastewater engineering. Okay. Yeah. The purpose of distribution, we'll start from the water distribution network. So the purpose of distribution network is, as I told you, is to deliver the water to consumer with appropriate quality and quantity and pressure. Uniform pressure should be there. The quantity that much we have promised, it should come. Suppose we have a 2 hours water supply in the morning, in evening we have a 1 hour supply, or suppose every day we have 1 hour supply in the morning, in evening. Like this, we have to promise that whatever the quantity should reach with the adequate pressure. So 7-meter pressure head you have to require for the for one floor, and if the rise is between 2-3 floor, then the pressure also increase. So for that you have a pressure gauge and you have to take the pressure head, which will be able to supply the precise amount of water during the firefighting. So these are the objectives we have to check, like the good distribution system is there. Clear things are there, the no cannot go without water supply during repair or any section of the system. All the distribution pipes should be preferably laid 1 meter above the sea level line. It should be watertight so as to keep losses due to the leakages in to the minimum. But as I told you, always water supply pipeline should be above from the sewer pipeline. Leakage, and it should be leakage proof also. Leakages and losses should be minimized. All the head losses, all the real losses and commercial losses should be minimized. Maximum altogether should be in the range of 15 to 20% maximum. If it is increasing, if the losses are coming 40 to 45%, suppose you are treating 15 mld water, if you are supplying 15 mld water, and 50% of this it is getting lost in their head losses, and even because of the leakages in the pipelines, right? Because of the threatening also, like some of the people are having a more than uh, 2 pumping stations, and they are extracting more water, right? So like this, some of the threats are there in piping networks. The apparent losses and real losses you have to take care, and their analysis is there. Energy audit you have to do it, water flow audit you have to do it. At the consumer end, you have to check every day, and then to check how much pressure we are getting it, and what are the quantity of water we are getting it every day, and the quality also we can check it. And then you have to check all the various pipe network also, so that the efficiency you can check it for the distribution network. All the lines and keys you have to check it, whether somewhere leakages are happening, and some pipelines are break and all that, right? All the walls, the connections also we have to check. Somewhere if you are not getting adequate pressure, then pumping stations are also required. So these are the things that you have to take care, and they are the ideal water distribution says we cannot compromise the quantity and quality of the water and pressure of the water. Yeah. So these are the how the things are working. We have an intake work, and then treatment works, and treatment we have done it. It started from aeration and pre-chlorination, then plain sedimentation followed by coagulation, then filtration we have studied, then disinfection was there. After disinfection, if there's a extra chlorine is dissolved, suppose, so dechlorination is required, so it will come to the surface, and then we have to clean it with the water from the water, and then we have to treat it with the water, and then we have to clean it with the water. So these are the things that you have to take care. And there the ideal water distribution says we cannot compromise with the quantity and quality of the water and pressure of the water. Yeah. So these are the how the things are working. We have an intake work, and then treatment works, and treatment we have mainly three types of distribution systems we talk. One is the gravity based. So all the pipelines are drawn throughout the gravity system. The pressure can be maintained through the gravity system. There is no pumping station. Another one is the pumping systems are required. Suppose we are having hilly areas and water has to lift somewhere from the ground. Then pumping stations are required. And one is the dual combined base. Some of the portions through the gravity, some of the portions from the pumping station. Now this is the water mains, distribution water mains that you have to draw now nowadays in sewerage, and that you can distribute, you can design the whole water distribution network. And through the SCADA waste software based mechanism, you can monitor the. It's a real based monitoring system, so you can assess the losses and how much pressure we are getting in that much of that pipeline, and what are the leakages are happening. So you can easily detect it. What is the real um, working based models are there like SCADA to operate the whole system. Now, our colonies and our communities are town planning, like town planning is also happening. So here we have to go through some the various branches. So I will talk later various types of distribution system and service pipelines. Then finally the leakages and consumer. This is the layout of distribution network. So generally the pipelines are laid down on the road pavement. As such, their layout generally followed the layout of the roads. We have to go for the detailed topographical survey, and you have to do the contour survey or surveying also. You have to record all the MSL levels. Based on this, you have to draw on all the we can see the pipe network. Pipe network means pipe material also. You have to select a diameter and all the hydraulic parameters. You have to check it while you are designing a water distribution network. So that is the another thing. In WaterCAD and WaterZem, you can design the whole network. Okay. So there are the four types of pipe networks, any one of which either singly or in the combination can be used for the particular place. These are the system like dead end system, radial system, grid iron systems, ring systems, or we can say the dead end system. A dead end system we have done it, that's a ring system. There are the four types of the distribution networks. So this is the dead end or tree system. Suppose this is the main pipeline for the distribution network. And these are the, and these are the submains. In the submains, these are the house. Again, we have another street, and their houses are aligned. So it will be in that form. Suppose we have started from here. It's the main pipeline. Now water is distributed like this. These are the pipe network that you are going to draw it in such a manner. Everywhere you have to optimize the pressure. Everywhere uniformly water supply should be there in each and every node. We say the node, every node, we want a uniform water supply. And pressure also you have to check. So M is the main pipe, B is the branch, and S is the submains, and this is the cutoff walls that you have given. These are the linemen here. He has to divert the flow. Suppose 7 to 8 water supply will be there in this zone, then 8 to 9 water supply in this zone, like this lineman will work. So first one, it is suitable for the whole town and cities having no definite patterns of roads. In this system, water flows in one direction only. The diameter of the pipe decreases at every 3 branches. These are the advantages. Relatively cheap method. Determination of discharge and pressure easier due to the less number of valves. What are the disadvantages? Due to the many dead ends, stagnant of water occurs in a pipe. This is the second system, radial system. These are divided into different zones. This is the radial system. See that this is the from here branch connection is given towards in a uniform manner. So this is M, main distribution pipe network. This is the submain network. 1 2 like 4, and after that connection will be given like this in a radial manner. The water is pumped into the distribution reservoir kept in the middle of the each zone. Here one reservoir, here one reservoir, here one reservoir. Like this, everywhere reservoir you have to kept. And the supply pipes are laid readily ending towards the periphery. The pressure calculations are easy in the system. Layout of roads needs to be radial to eliminate loss of head in the bends. These are the advantages. It gives quick service. Calculations of pipe size is easy. These are the disadvantages for it. And the third one is the grid iron system. You see that this is the main pipeline. These are the submains and these are the branches. So we have to work in a grid, closed loop. There's the loop and nodes here. Water is going, then closed loop is you are maintaining. So like this closed loop, and then if water has to supply in another next line also, then you can supply it. So everywhere it is a closed loop, one loop, two loops, and submains. You can see that everywhere there's a closed loop. That's all. Yeah. So ask others to join very less announcements. Yeah. Okay. So like this, the system will work. It's in closed loop. There's a node and connections in loop. I will come for the loops and nodes later on. It is suitable for cities for rectangle layouts in where the water mains and branches are laid in rectangle. Can you hear me, Nisarga? Is it audible?
Yes, sir. It was
No. So from the main waters enters the branches at all the junctions in either directions into the submains of the equal diameter, like this. At any point in the line, the pressure is balanced between from two directions because of the interconnected network of the pipes. So like C meters, main branch, submains, and cutoff valves. Okay, these are the advantage and disadvantage. In case of repair, a very small portion of distributions are well affected, and every point receives supplies from two directions and with higher pressure. Additional water from the other branches are available for firefighting. There is a free circulation of water, and hence it is not liable for population due to stagnation. Water is kept in good circulation due to the absence of dead ends. These are the advantages. Disadvantage: more length of pipe is required, number of valves are needed, hence there is an increased cost of construction. Calculation of size of pipes and working out pressures at various points in the distribution network is complicated. Exact calculation of size of pipe is not possible due to the provision of valves on all branches, means the more losses will happen. This is the last ring system. The supply main is led all along the peripheral roads and submains branches out from the mains. You see there. This is the main pipeline. It is equally distributed in two directions. This is your layout, complete colony layout. Now water will go first here and then here equally distributed. It depends how many supplies are there. And then first it will go like this in this uniform manner, and finally it will join this main pipeline. So here also it will comes like this and it will join further the main pipeline. So like this water will go further also. Now here is the straight rectangle layouts, 1, 2, 3. Water will go from here also, water will go. So water supply will be from two directions. Like this water supply will happen. And these are the points here, 1, 2, 1, 2, 1, 2, like this. Once we go for the Hardy Cross method for designing of distribution network, you will understand more about the nodes and all that. What are these points and all. The system also followed the grid iron system with the flow patterns similar in characteristics to the dead end system. So determination of the size pipe is easy. Supply to the inner pipes is from the mains around the boundary. It has the some disadvantage as the grid iron system. Smaller diameter pipes are needed. Water can be supplied to any point from at least two directions. Yeah. These we have discussed just now. We have a gravity system, pumping system, and combined gravity and pumping systems. For the efficient distribution systems, adequate water pressure required at various points. That is the key requirement. Depending upon the level of source, topography of the area, and other local conditions, the water may be forced into distribution system by two ways. Gravity in pumping. Gravity is suitable when the source of supply is at sufficient height, more reliable and economical. Low pumping stations are required. The pumping and energy cost will be high. The water head available at the consumer is just minimum required. The remaining head is consumed in the friction as well as the other losses. So this is the pumping system where the town is situated here. This is the water reservoir. This is the gravity system actually. So treatment on the top and then this is the gravity system. So directly water will come there without applying any intermediate pumping station. Now for the pumping system, the treated water is directly pumped into the distribution main without also called pumping without storage systems, and high lifting pumps are required. The power supply will be from the so disturbances and all that. Energy cost is also high. So here you see there that this is the source of water supply, intake pumps, clear water reservoir. Water has to supply into the town, and then because head losses are there, and static pressure head is also we have to maintain, so that we need intermediate pumping station here. So constant pressure can be maintained in the system by direct pumping into mains. Supply can be affected during power failure and breakdown of pumps also. That's why two pumps are required for the standby mode. During fire also, fire safety also, we need a fire reservoir. The firefighting demand we have to fulfill. The water can be pumped into the required quantity by stand or by units. This is the combined system, combined gravity and pumping, partially through the pump pipe, partially through the gravity system. So suppose this is a reservoir, overhead storage reservoir on a certain height. The simple tank that you know that. The source of water intake and clear water, and after that there's a clear water reservoir, CWR. From there, water is on a certain height. Static water has to maintain here. Now here the calculation has been given for HF, the static water head, Darky Westus formula. So, and town is like this, suppose. So the gradually the pressure will decrease if you go away towards the consumer end. So that's why the pumping station, because somewhere in the near of the tank, near of the reservoir, pumping is not required. So the gravity water will supply because sufficient water head is maintained because of we have put a water on a very height, 30 to 40 meter, 40 feet height, 20 to 30 meter height actually. This tank. So like this in a clear water reservoir. So water may be supplied to the consumer by either of the two systems. One is the continuous system, another one is the intermittent systems. By the name suggests itself, continuous system means it's a base system, 24 hours water supply you will get it. Wherever you will open the tap, water will be there, right? In this system, sample of water is always available for the firefighting, and due to continuous circulation, water always remains in a fresh condition. In this system, less diameter of pipes are required, and rusting of the pipes will be less. Loss will be more if there are leakages in the system, because 24 hours water is available in the distribution network. Of course, wherever the leakages have happened, 24 hours water will be leakage from the broken pipe. So leakages will be happening, of course, more. But other perspective from the service point of view, is best. Intermediate system, if plenty of water is not available, the supply of water is divided into zones, and each zone is supplied with water for fixed hours in a day, or on alternate days, as I told you. As the water is supplied after intervals, it is called as intermittent supply, and the system has following disadvantage. Pipelines are likely to rust faster due to the alternate wetting and drying. More wastage of water due to the tendency of the people to store more water than required quantity. And through water, the access to collect the fresh water each time, the repair water can be easily done in the non-supplying hours. Like this. Okay, these are the some disadvantage and advantage for the intermittent system. More wastage happen due to the water tendency, as I told you. Required contain the waste to collect the fresh water each time, and the repair water can be easily done. Okay. Now, storage capacity of the distribution system, you have to construct various reservoir for storing intermediate storage for the water, and for maintaining the balance also, for maintaining the adequate pressure. So one is the balancing tank, a balancing equalization storage, then breakdown storage, fire storage, and distribution reservoir. Distribution reservoirs are having two types. One is the elevated storage reservoir, ESTRs. Yeah, sometimes we called as overhead storage reservoir. Another one is the ground level storage reservoir, GLSR. GLSR as well as the OHSR. It will comes in the distribution network. So distribution reservoirs are also called as service reservoirs, are the storage reservoirs which stores the treated water for the supply water during emergency, such as during fires, repairs, etc. And also to help in absorbing the hourly fluctuations in the non-supply of water. Due to the elevation with respect to ground, the surface is sometimes reservoirs are called as a overhead storage reservoir, OHSR. Okay. Yeah, sometimes clear water reservoir. The both are clear water reservoir. All things are clear water reservoir only. There's no dirty water and untreated water storage. This is one town where the water distribution network has been drawn. Just typical 3D drawing, animated drawing of the water supply. All points are given. So raw water main starting from one. Here somewhere their river is there or lake is there. The source of water, surface source or maybe surface or maybe groundwater source. Water is taken through the rising main pipelines, and then it will come through the intake structure through the various screens. It will be the intake structure, and from there water has to be treated by various operations. And here this is the complete WTP, water treatment plant. And then water is to be stored, clear water. There is a clear water storage, CWR, and from there water has to be distributed. Yeah. They are the function of distribution reservoirs, and location and height of distribution reservoir play an important role. That's why we have to, while you are designing, you have to maintain all those things. Why distribution reservoirs are required? To absorb the hourly variation in demand, to maintain constant pressure in the distribution mains. Water stores can be supplied during emergencies. Location and height of the distribution reservoir should be located as close as possible to the center of the demand. Water level in the reservoir must be at a sufficient elevation to permit gravity flow at an adequate pressure as to maintain. These are the surface reservoir. Not going into details because there's a time constraint. Yeah. These are the design of the tanks, reservoirs, and these are the advantage and disadvantage of this. And material also you have to select it for the distribution network, HDPE tanks or ZI tanks, or maybe you are using cast iron pipe, right? You are using a plastic PVC pipe, PVC pipe, depend what material you are using for the distribution. While following the like various advantage, you have to check the various mechanical properties of various pipe networks as you have discussed in sewage treatment, sewage wastewater engineering. The same way you have to do the analysis. Why same jagah, same place. So various mechanical properties, durability, strength, reliability, material, temperature, strength, all those parameters you have to expansion properties of a material. These all those things you have to take care. RCC tanks, then various analysis we have to do which material is suitable and all that. Okay. This elevated storage reservoir we called as OHSR. So this design you have to do in maybe RCC or steel structure you can go. They are the various component for it: inlet and outlet, overflow pipe and discharge into a drain, float goes gaze, indicating the pipe and depth of pipes, automatic device to stop pumping when the tank is full, manhole ladder, all those things. This is the overhead OHSR, elevated storage reservoir. Yeah, we can see the overhead storage reservoir and pumping stations, water treatment plant. Water has to be stored in OHSR. A simple tank that you have seen in your colonies. Now water has to be discharged to your household. Yeah, GLSR, ground level storage reservoir. Balancing storage reservoir, as I told you, the objective is clear for it. We have to store the water for fluctuation demand, and the breakdown storage also often called as emergency storage is the storage preserved in order to tide over the emergencies posed by the failure of the pumps like steel and any other mechanism driving the pump. A value of about 25% of the total storage capacity of reservoir, or 1.5 to 2 times of the average hourly supply you have to maintain for the breakdown storage. Now we'll come for the design part of distribution network. This the design of water distribution systems must go under through different studies and steps. Number first is the design phase. First is called as in design phase. First is called as the preliminary studies, then network layout, and then third is the hydraulic analysis. While you're going to design a distribution network, various stages you have to cross it. Now, first is the design phase, where the detailed topographical contour map, contour of the graphical level various elevation benchmark if you have to do the study. Before starting the actual work, there's the prelim, there's a survey work actually. You have to do the various survey alignment and layout, everything. You have to define that, and you have to find out how much area is there, what are the total coverage, existing coverage of water supply, how much you are going to propose it. These all analysis you have to do this. Water demand calculation you have to do it. Future forecasting of population that you have to do it, as in the last year's WST we have explained all those things. Okay. After that, we have to contour lining, controlling elevations. You have to do this. Then digital map showing present and future houses, streets, plots, and so on. Population, everything, all data it will show. Location of water sources so that to help locating distribution reservoir, existing water reservoirs, surface source as well as subsurface source you have to identify. Now we'll come for the actual design of distribution network. This is the pipe network analysis, most feasible method, which is called as Hardy-Cross method. Okay, so there are the two basic. I will come here. Design criteria. First, we'll go for the design criteria. Then I will talk about the Hardy-Cross method. So while you're going for the pipe network analysis, Hardy-Cross method is very effective. Okay, I will talk later once I will go for. These are the things for you have to understand for the design criteria. Are the design limitations required to get the most efficient and economical water distribution network? Pressure, design period, velocity, head losses, pipe sizes, average water consumption, all the water demand calculations, firefighting water, how much it is required, all calculations you have to do it. Okay. So these are the design parameters. How much pressure is required, optimum pressure at the distribution network. 7 meter, 6 to 7 meter water head is required at one house. Above the 2 stories, 3 stories, 14-meter water head is required. So these are the various things, various parameters. Design period for the distribution network, 10 to 15 years. You have to take it at least for the pipe network, right? How much velocity of flow is required, all the hydraulic parameters, how much head loss should be optimum, what should be the pipe size, so the optimum water head, or we can say the flow rate can be maintained in the pipe network. All those things you have to do it. Now I will come for the analysis of distribution network, then Hardy-Cross method will do it. The first is pressure drop head loss HF that you have to study. Flow rate discharge in each pipe Q you have to study. Second is the dead end layout analysis by simple pipeline. So these are the methods that I will tell one by one. Darcy-Weisbach equation for finding the head losses HF 4FLV square upon D into 2Z. Done in applied hydraulics laboratory. Then continuity equation, because we are dealing with a closed conduit pipe network. So Q is equal to A1, V1 is equal to A2, V2. That equation you have to consider for it. Darcy-Weisbach equation you have to consider for it. Then flow rate equation. Bernoulli equation also quite frequently used here. It's a closed channel flow. Third is 1, 2, 3 pressure drop head loss HF, dead end layout analysis. Third one is the grid iron radial layout. Complex pipe networks are best analyzed by the Hardy-Cross method. So if it's having a complex network, then we'll go for the Hardy-Cross method. It will give the exact approximation, and we will be very, we can say, the near for the results. Okay. So yeah. Now the quantities of flow and head losses in the various pipelines and resulting residual pressures in any pipe network, the following two conditions must be satisfied. Now the Hardy-Cross method I'm talking, there are the two conditions for it. Number first, the algebraic sum of pressure drop around a closed loop must be zero. The algebraic sum of pressure drops around a closed loop must be zero. There can be no discontinuity in the pressure. Number second, the flow entering a junction must be equal to the flow leaving that junction. The law of continuity must be satisfied. So Q in is equal to Q out. Yeah, A1 A in into V in is equal to A out into V out. So jitna whatever the flow we are maintaining at inlet, it should be equal to the outlet in ideal conditions without any losses. In really, we will be having 15 to 20% losses at outlet. Of course, the same quantity of water will not get in at the consumer end. Okay, but in ideal conditions, the pressure drop all the pressure drop should be equal to zero. So these are the two conditions. So these are two basic principles by method of successive approximation. The widely used method of pipe network analysis is the Hardy-Cross method, and it's quite useful. We'll talk about the Hardy-Cross method. Closed complex pipe network, trial and error procedure. Head loss is a function of discharge, and head loss is proportional to Q to the power X here. You can write H is equal to K into Q to the power X, and K will be the head constant. And HF, you will get it through the Darcy-Weisbach equation, that is FL Q square upon 12.1 into D to the power 5. There are the two conditions, as I told you. At any junctions, flow towards junction is equal to the flow away from the junction. Q in should be Q out, one condition. The algebraic sum of all the head losses a pressure around a closed loop should be zero. The summation of the all head losses should be equal to zero. So two conditions, the Hardy-Cross method will work on two conditions. These two conditions, the summation of the pressure head equal to zero and Q in should equal to Q out. Okay, and this is the ideal equation for it. So I just derive it simply how the things will happen. This method consists of assuming a distribution of flow in a network in such a way that the principle of quantity is satisfied at each junction. A correction factor to these assumed flow is then computed successively for each pipe loop in the network until the correction is reduced to an acceptable magnitude. If QA is the assumed flow and Q is the actual flow in the pipe, then the correction Dale is given by Dale is equal to Q is the actual flow and this is the assumed flow. So Q minus QA, you can write it Q is equal to QA plus Dale. Now expressing the head losses HL is equal to K into Q to the power X as we have told. So we have the head losses in the pipe. So you can write it HL value, you can replace it K into Q to the power X. Q is there, then QA plus Dale to the power X. You can further solve it and K into Q in E to the power X, like this it will go in approximation. So you can go integration or summation directly, summation of all the values. As we have told, around a closed loop, the summation of the head losses must be zero. So summation of head losses, this is basically a head loss. This is basically a head loss actually. because actual minus ideally you are minusing it. So head loss you will get it. So summation of all head losses as per the definition should be equal to 0. Then they have calculated in such a manner. And Dale is the same as for the all the pipes of the considered loop. It can be taken out of the summation, and then you can further solve it, and then finally Dale value you can get it. So Dale value you will get it Dale here. You are, if you're segregating some minus summation of the k into qa to the power x divided by summation of the x into k into qa to the power x minus 1. So Dale is the same sign. It's the directional characteristics. You have to see the flow directions, negative and positive. I will go in detail. So in all the types of the loops, the denominator of the above equation is taken as the absolute sum of the all the individual items in the summation. So it will become finally positive. So this is HL is the head loss for the assumed flow. Okay. The equation to solve pipe network must satisfy the following condition. Summation of the Q is equal to 0, as I told you. There are the nodes, loops, and pipes. All head losses must satisfy the Moody and minor losses, frictional corrections. And here I have not seen. Okay, I'll go further. Just 2 minutes. Yeah, this one. So these we have studied everything. I will just tell you about these equations we have derived it for the fire demand and all that. And velocity you have to take it like this. Pressure first we'll go for this. These are design criteria. Here velocity should be 0.6 meter per second to prevent the sedimentation, not be lower than 3 meter per second. As for the design criteria we have mentioned no these design criteria. I'll just tell you the standard value, then I will move for the Hardy Cross method. Not be more than 3 meter per second to prevent the erosion and high head losses. Commonly used value to 1 to 1.5 meter per second. Pressure should be in that range. Pressure in municipal distribution systems ranges from 150 to 300 kilopascals in residential districts with the structures of 4 stories or less than 4-story buildings, and it should be 400 kilopascal in commercial estates. Waterhead. In general, for any nodes in the network, the pressure should not less than 25 meter of waterhead. The maximum pressure should be limited to 70 meter of waterhead. Pipe sizes depend based on the quantity of flow, based on the flow rate, and all the based on the demand actually. So small scale and then high scale values are given for the larger district. Based on the population, the pipe diameter will be decided. It's a hydraulic parameter. Head losses optimum range should be 1 to 4 meter per kilometer. Maximum head loss should not exceed 10 meter per kilometer. Design condition with the standard design. Average water consumption, all those things. Then network layout we are studying. Pipe network, and then complex analysis. This is a Hardy Cross method. Here, yeah. See here. Now node, loops, and pipes. We have started from here 1, 2, 3, 4, 5. It's actually these things for understanding and for learning those things we need a time. 2 hours duration is not sufficient, but still I try. Just I will share these PPTs and module everything. You just go through that. It is easy. Just try to you study these theory part and design part, and then try to attempt the numericals. Then you will be very close. So that this is the one loop. This is loop 2. This is loop 3rd. This is loop 4th. How it is the loop? 1, 2, 3, and then it will be closed connection. Loop means closed loop should be there. Loop should be closed. If it is open, then loop should not be open. So second is seeing there is a loop closed connection. Water is flowing there, water is flowing there, water is flowing there, and water is flowing there. Here it will meet. So one closed loop. So one closed connection will be a one loop. Here also, here then water will be closed. Loop 3rd. And here also, like this, you have to decide the loop 1, 2, like this, the loop will be closed. So they ask a lot of questions on distribution network, water distribution network, especially on Hardy Cross method. So it is very important to understand the loops and all that. Okay. This will be one node. This will be one node. These are the nodes. The junction point will be the node. Yeah. See, this is node. C is the node here. The loop we have explained. Here also I is the node. Z is a node, A is a node. These are the nodes. Yeah. So Hardy-Cross method, this method is applicable to the closed loop pipe networks, a complex set of pipe in parallel. It depends on the ideas of head balance method, was originally developed by Professor Hardy-Cross. You see there, this is Q in actually, and this is finally Q out, Q4. So you can representing here Q1, Q2, where is Q3, and Q3 and Q4. Finally, water will be coming out. So water is flowing, distributing in two channels, Q1, Q2. Suppose here Q11 and Q12 like this. Here it is Q2, so Q21 and Q22 like this. It will be distributed equally. And then finally there's water is flowing. This is water flowing. It is closing. Means one loop. This is also one loop. This is also another loop. Like this, various loops will be forming. Yeah. These assumptions, as I told you, these two assumptions always you have to take care. Head loss, summation of all head loss should be 0. Sign is very important. Around any loop in the grid, the sum of the head losses must be equal to 0. Conventionally, clockwise flow in the loops are considered as positive and produce positive head losses, and the counterclockwise flows are then negative and produces negative head losses. This fact is also called the head balance of each loop, and this can be valid only if the assumed Q for each pipe within the loop is correct. The probability of initially guesses all flow rates correctively is virtually null. Therefore, to balance the head around each loop, a flow rate correction factor Dale is introduced for each loop in the network should be computed, and hence the sum iteration scheme is needed. This Dale value you have to note it. You have to we can determine actually. I told you, here. I will just go. This is my previous right here. Where is the Dale? This Dale is nothing but it's a correction factor. Where this I have explained. Yeah, in there you will see that. Yeah. This this correction once you design, then you will add this in the flow rate in and flow rate out, and you will balance the layout. So after finding discharge correction Dale, one for the each loop, the assumed discharge Q naught are adjusted and another iterations is carried out until all corrections to be done become 0 or negligible.
Sir, you're not audible.
So these are the things how we have to do it. Now, no need to do a big calculations. On smaller things you have to do it. Only the iterations you have to do go till that you will satisfy the condition for the Hardy cost. Okay. So two constant, Hazen-Williams constant as well as the Darcy-Weis's constant. For Darcy-Weis batch n is equal to 2 and Hazen-Williams n is equal to 1.85. Rather than this small examples, you have to do it. You have to move these iterations and you have to find out Dale 1 again. You have to move it. You have to go till then, you will satisfy the equation. The second example, as I told you, these things Dale 1, Dale 2. Is it audible, Pranati?
Yes, sir.
Okay. Like this, we have to move for it. Like this, we have some of this Hardy cross method in distribution network. Now I will move for the wastewater engineering. Okay. So this is done for the water supply engineering point of view, water supply and treatment engineering point of view. Go for the I'm moving for the wastewater engineering now. So some of the things are common, like I'm talking about the characteristics part. Of course, the sewage water is more complex than the normal municipal water supply, municipal normal water, surface water, because sewage water contain more impurities. The BOD and COD will be more toxic, and other physical, chemical, and biological characteristics are quite complex. So of course, the treatment will be also higher. Higher degree treatment you have to provide for the wastewater engineering. So what we are going to cover here in this part, in the wastewater engineering, we're talking about the design and planning part of the sewer network, and what are the various hydraulic design parameters, and what are the various iterations, and what are the various formulas are required for designing purpose. What are the design parameters that you have to take it for the designing and planning part? What you have to do, how to do the design, how to move for the planning phase to the actual construction phase for the sewer network. So there are the two things are there in wastewater engineering. One is the sewer network design. Once you design a sewer network, then you have to take this water for the respective sewage treatment plant. Okay, and the sewage treatment plants. Then we'll talk about the complete treatment components of sewage treatment plants, like preliminary treatment, primary, secondary treatments, and followed by the miscellaneous treatment, all that, and followed with the discharge treatment also. Okay, so what we'll be covering here, the sewerage system designs, quantity of domestic wastewater, primary and secondary treatment, we'll talk about it, effluent discharge standard, sludge disposal, reuse of treated sewage for different applications. Anyway, luckily we are having the same subject in our BE courses right now. In this semester, we are teaching the same subject, and we already moved for the treatment part. We have completed the whole because there we are getting a sufficient time for explaining the concept in details. So there we have explained in detail about the whole the designing and planning part of the sewer network, material selection of the sewer network, what are the hydraulic parameters, and what are the design factors that we have to take it, what are the iterations and various formulas are required for designing, how to go for the sewage flow rate and various dry weather flow and wet weather flow conditions, right? All those things we have studied, but here we will quickly go from the gate point of view. And then, yeah, first we'll start from the estimation of dry weather flow. I'll just quickly go for the formulas. I will just revise it because you are in the same semester and you already know all these things. We have gone through in detail in the previous semester. So what we'll be covering here, so there are this dry weather flow here. in wet weather flow in non-peak monsoon season, where the storm water is not there in the non-monsoon times. In India, we have 4 months of season of monsoon, remaining 3 months called as max. And we have wet weather flow, which is a storm water flow actually. Storm wet weather flow, storm water flow, and we have to manage both. Actually, a sewage water is generated everyday basis and will be throughout the year. And sometimes in a rainfall season, if wet weather, if rainfall is also occur, then surface run of water, storm water also should be included in that. And we have various types of systems for the sewer network that we'll talk about the sewer systems. So driver flow, how to get it? The Q driver the flow is equal to what are the population you are getting it, what are the population of the town into per capita sewage flow. Generally, the 80% of supply will be called as we are taking as a suppose if we are supplying a water for a respective town 5 mld, so 80% of 5 mld will be a sewage water, right? 75% to 85%. So the rate of water supply is generally 135 LPCD to 250 LPCD in our Indian conditions. So based on this, you can calculate the flow rate, how much water demand is required, how much estimation of water is required, and then once you get the water estimation, if you want to get the sewage flow rate, the complete quantity of sewage, the 80% of whatever you are getting will be the sewage flow rate. So in meter cube per second, generally it will give in MLD. You have to convert into meter cube per second. So per capita sewage flow is equal to per capita water supply multiplied with the factor. Factor means 80% or 75%, whatever you are taking it, approximation. So 75% of the per capita water supply will be the per capita sewage flow. This is a simple calculation. Now factor is to account for percentage of water supply converted into the water, 75 to 80, 70 to 80%, as I told you. Supply to community becomes wastewater and reach sewage as below. The QW DWF will be the population into per capita water supply multiply with the factors. Finally, you will get Q like this: how much population multiply with per capita water supply multiply with the percentage of sewage generated. That is, you take as suppose 80%, so 80 divided by 100, you will get in Q dry weather flow rate. But it will be in MLD, you convert it to meter cube per second. Multiply with 10 to the power 6, divide by 10 to the power 3, multiply with, as I told you, 24 into 60 into 60. 86400. Second is the wet weather flow. To estimate storm water from urban area, urban catchment, rational formulas are used. One is the common formula for wet weather flow. Q wet weather flow is equal to A into I into R divided by 360. This is the rational formula. A is the catchment in hectare. I is the impermeable coefficient factor or runoff coefficient. I is I you can calculate runoff divided by rainfall. R is the rainfall intensity in mm per hour. So I you will get it summation of the A into I, AI into II divided by summation of the A. You have done it in your this semester calculations, in this semester regular studies. And R you will get it 25.4 into A divided by TC plus B. TC is the time of concentration in A, and B, A and B are the constant whose values are dependent on the duration of the time. So these you have done it. So I just quickly go for the that what we have discussed, what we have studied, go through this, and then I will move for the treatment part for the series. So these we have discussed. They are the wastewater engineering, municipal water, and industrial wastewater. They are the various terms like refuse, garbage, sewage. I have a word PPT. That will be better. I need to see this. If you have, Just quickly, we'll revise the formulas. I'm not going into too much of details. Okay, yeah, since we have already studied and we are right now regularly also we are studying. So these are the various definitions for the sanitation, bathroom, kitchen, laboratory, wastewater sources. What are the sources we have hanging for the wastewater? These are the various definitions for garbage, sewage, stormwater, subsoil water, and sewage. Right. So garbage will be the waste, here solid waste, which is coming out from a daily household activities. Sewage is the typically wastewater, which is coming out from a toilet and kitchen activities and all together. So it will toilet flush and everything, washing, drinking, everything. From the all the daily operations, the water is coming out as sewage water. Storm water is a rainfall water, precipitation. The rainfall water is coming as a surface runoff. Subsoil water, the water is in moisture in the soil, and the salis is together except for the toilet water. Salis will be. So, and this is the fresh water and all that. These are definitions. This is the garbage and the sewage. Is fresh sewage, the term used to indicate the sewage which has been recently originated. Aim of sewage disposal is well known for proper disposal of human except for safe places to take out all kind of wastewater into the locality, to stop the waterborne diseases and to prevent that, and so that everyone wants a hygienic and sanitary. We want sanitized cities, so everyone wants to be stay in a clean environment. That is necessary also, for we want to survive in the clean environment. So that's why wastewater treatment is necessary. There are the methods for sewage disposal, conservancy system, and water carrier system. So method of sewage disposal is the conservancy systems. Toilets are much economical and all that. It was conservancy systems are old systems where there is no particular sewage treatment plants. They will be having a septic tanks and all that. Normal, it is suitable for the small towns and all that in villages, and it is the old practice. The storm water goes in open drains and sewer section will be small. The night soil which is buried can be used as a fertilizer after 2 to 3 days. There's open burning, open dumping actually for the sewage water. And yeah, these are the comparison of conservation system and water carrier system. Water carrier system that we use it nowadays in our sewage treatment plants. Sewage is treated up to the required degree of sanitation. Less area is required as compared to the conservancy system. There is no bad smell in order. It is completely controlled environment we use to treat this sewage water and water carrier systems, applicable for both the storm water as well as the dry weather flow conditions. Right, industrial sewage also can be included in that. So there's various advantage for this, and there's various definitions. What is sewerage? A network of pipes, pumps, and force mains for the collection of the wastewater and for sewage from the communities called as sewerage. And there's a domestic, industrial, and stormwater also will be included in sewage. That we have done it. And types of sewers used in collection of the sewage. So these are the branch sewers, the submain sewers, lateral sewers, main sewers, outfall sewers, and then combined sewer, relief and overflow sewer, and trunk sewer. What is happening? Branch and submain sewer, then branch and submain sewers are connected with the lateral is connected from the to the main sewers, and main sewers are connected to the trunk sewers, and trunk sewers are connected to the building is going through the finally in the sewers which operate in the small sewer delivers into the main sewer, then main sewer discharge from the few branches connected to the trunk sewer will come finally, and then finally trunk sewer is connected to the outfall sewer, which will take outfall sewer will take all the wastewater from the city to the respective sewage treatment plant directly. It is the largest diameter. The transport sewage of the city to the point of the treatment unit. The combined sewers means including with the domestic sewage water as well as the storm water, rainfall water. So this is called as a combined sewer. Sometimes industrial sewage also included in that. Then there's a combined type of sewage systems. So that we have studied all those things. So I'm not going in details. Types of sewer used in collection systems. These are the design part, main sewers, how it is connected and how laterals are collected with the submains and all that. So water carries demerits and merits we have studied. Now collection of sewage is done. Types of sewers used in collection of the sewer. As I told you, the main this is the main house drainage. Lateral sewer is connected. Lateral sewer is connected to submains and ground sewer. Here also lateral sewer is there. Then it is connected to the we can say the main sewer. Main sewer is connected to the trunk pipeline. And trunk is connected to the finally outfall sewers. Like this, it is there is a wastewater treatment finally. So there are the three types of sewage systems: separate sewer, partially separate systems, and combined sewer. Separate systems where the only domestic sewage is treated separately. Partially separate means sometimes we can say the this table like this. Yeah. So table for when the only the domestic sewage water is included, and advantage and disadvantage of this combined sewers. So both will be included. This is the typical layout, how the things are happening. Combined sanitary wastewater and stormwater included. And finally, it will go for the treatment and disposal. These are the advantages for it that we have studied. Partially separate and wastewater flow rate. I will just go for the dry weather flow rate and wet weather flow rate. Dry weather flow rate, as I told you, uh, the sources, the flow rate that of the sewer that would normally be available during the non-rainfall period. The additional flow rate that would occurs during the rainy season is called as wet weather flow. So I'm not taking too much of time that we have done it. If you want to get the value of maximum flow rate, this factor you have to add it. Maximum flow rate will be equal to 2 into average daily flow rate, and the minimum daily flow you should be equal to 2 by 3 of the average daily flow. Factors affecting the dry weather flow: rate of water supply, population growth, type of area served, rate of water supply, population growth. This is the FSI index, total area covered in all the float divided by area of the plot. FSI index is required for the to understand how much wastewater is generated from the particular area. Suppose a multiplex, there's a the domestic flat there colony. So multi layers stories are there. So for this, our total area covered divided by area plot, you can get it. This is called as the floor area index. Floor area. So build up area and FSI index is required. Then population density is also play a very important factor. We have done these calculations in the classes. Infiltration of ground, how much water is infiltrated during the surface runoff, that is also play an important role. So infiltration rate, you have to calculate for it. So infiltration again considered as a losses in a sewage water sewer network. So we don't want infiltration, we don't want exfiltration also, because this can lead to groundwater infiltration and exfiltration of sewer network. We don't want both the conditions. Infiltration of groundwater depth of sewer below groundwater level, size of size of sewer, length of sewer, nature, and type. Infiltration rate, you have to consider it. In suppose they have given liter per hectare per day. So like this infiltration rate, you can consider it. Diameter, length basis. These are the reasons for the groundwater infiltration: defective pipes, leaking pipe joints, poor connections, cracked manhole walls, and all that. Various flows are there in sewage flow. There are some maximum flow rate will be Q max and minimum flow rate will be Q minimum. And there are the formulas, empirical and rational formulas for getting the values. Suppose you want a Q max, there's a Babbitt formula, 5 into Q average divided by P to the power 0.2. Population should be in 1000. Harmon formula Q max will get like this. So, yeah. Various ratios you have to calculate it: Q minimum by Q average, Q max divided by Q average. So, this variation depend because it's a climatic factor. So there are the 4 seasons in India. So based on this, we have to assume the variations of sewage flow. You have to fluctuations you have to consider throughout the, suppose October, November, in March, April, what should the flow? October, November, in March, and April, what should be the flow will be considered, right? And then minimum rate of flow will be considered in December and January. Maximum rate will be considered during June and July. It's a peak summer season, like this. The peak flow, that is very important. The peak factor has to be considered. Suppose average daily flow should be considered as a 70 to 80% of average water consumption. As I told you, average daily flow should be a 75% of average daily demand of the water consumption. That should be 0.75 average daily demand. The flow in sanitary sewers vary seasonably, monthly, daily, hourly, right? That also we have to consider. So the maximum daily flow, maximum hourly flow also we have to calculate it. Suppose maximum hourly flow should be equal to 2 to 4 of the average daily flow, and maximum daily flow should be equal to 1.5 of the ADF. So 1.5 is the peaking factor, 2 to 4 is the peaking factor, 0.75 is the peaking factor. So peak factor always give the correct estimation. So maximum daily flow should be 2 by 3 of average daily flow, and the minimum hourly flow should be 1 by 3 of the average daily flow. These are the peak factor values for the various connections: domestic sewer 6, lateral sewer 4.6, branch sewer submains 3, main sewers 2.5, trunk or outfall sewers 2. So a standard values for the design pyramid or designing of the sewer pipe networks. So peaking factor for infiltration should be in the range of 1.5 to 2, right? So I'm just quickly revising because you already know all those things because we have done it. Yeah. So minimum flow is maximum or lateral sewers. Since these sewers get the house drainage directly, Q minima should be 2 to 30% of Q average. Main and trunk sewers, Q minima varies in between 40 to 60% of the average flow. The overall variations between the maximum minimum flow is maximum in lateral sewers. Yeah, here this is important. The overall variation between the maximum and minimum flow is maximum in lateral sewers and minimum in main and trunk sewers. We have gone through the detailed discussion in the classes about all those things, so I'm not going for it. Qmax to Q minima should be 6 to 8 for the lateral sewers and 2 to 4 for the main and trunk sewer. These are the standard ratios. Okay. Sustained flow should be in the range of 0.45 meter per second, and its flow should be assumed 1/3 of the average flow. So now wet weather flow. The factor affecting the wet weather flows are catchment area, ground flow, permeability of the ground, extent of impervious area, and rainfall intensity. These are the things. Estimation of quantity of storm water. There are the 2 methods. One is the rational method. Another one is the empirical formula method. हाँ हाँ वो उधर का गेट खोल के रखना है. हाँ खुला रहेगा ना. ठीक है. There are the 2 formulas, rational formula, another one is the empirical formula for it, for getting the value of storm weather flow. So I just go for it. Rational formula. Yes. So our unit should be in mm per hour. Okay. And if you want to go for the unit. So hectare to you want to convert into meters square, then you have to divide with the factor into the 4. Like this, you can do it. So A into R divided by 360, you will get it. K will be 1 by 360. This is the rational formula is expressed in the common term. So this we have done it. Okay. So just skipping depending factors, permeability coefficients. The Kushling impermeability coefficient I value will depend on the surfaces. So various surfaces values it depends. So average permeability factor, you can take it like this. Suppose we have multiple areas. So summation of all the areas multiplication with the impermeability factors responding. Suppose A1 area is having impermeability factor some value. Like this, if you have to go summation of all the AI, summation of the all the AI divided by summation of the A, you will get the runoff coefficient. So C will you will get it in such a manner. Concentration. So time of concentration is nothing but time of flow, addition of time of flow plus time of entry. So there's a time of flow or time of entry of the runoff and time of flow of the runoff. Both the how much time we will be taking total is called as the time of concentration. The unit for the rainfall intensity is mm per hour most of the cases. Sometimes it is in centimeter per hour. Intensity of rainfall, there's some general formulas. So R in that Ri value, intensity of rainfall value, you have to take 25.4 into A divided by T plus B. This T is the time of time duration in minutes, or it will be equal to time of concentration only. A, B, and B value you have to decide it based on the United States Ministry of Health recommended. If the duration of a storm is 5 to 20 minutes, then A value 30 and B value 10. While you are doing the numerical, you have to do this like this. Yeah, is another formula for the heavy and frequent rainfall. Ri value you have to determine. If the storm occurring once in a year, then this formula you have to use. If a storm occurring during once in a 10 years, then this formula you have to use. The various empirical formulas. Kuchling formula. This is very common for the rainfall intensity. So a storm occurring once in a 10 years, then this formula you can use it. The storm occurring once in a 15 years, this formula you can use. Time of concentration, as I told you, it's a summation of time of entry and time of flow. Time of concentration is defined as the longest time without unreasonable delay that will be required for a drop water to flow from the farthest point of the drainage area to the point of concentration. So time of entry plus time of flow, you will get it. Time of flow, you will get it distance divided by velocity. Time of concentration Tc is equal to the inlet time T naught plus the time of flow, the same way. Okay. So according to Lloyd-Davis, the total volume of storm water is proportional to the maximum flow rate. The total discharge of storm water is proportional to the maximum rainfall during the time of concentration. So these are the hydraulic design parameters that you have to take care. So Lloyd-Davis formula says Q will be 1 by 360, 60 R upon T to the power dc into A into Y meter per second. So that also, if they ask, then you can go through this formula. For the duration of the storm T less than time of concentration, if T is less than Tc, then you have to use this formula. If T is greater than Tc, then you have to use this formula for getting the value of I. If the catchment area is more than 400 hectare, then the following empirical formulas can be used. These are the formulas, Igneous tablet. We have done it in the classes, so you can go through this. These are the formulas. These are the empirical relations. We don't have any derivations for this. Okay. So directly you will get it. Nothing is, it's a slope divided by area, and this R is the rainfall intensity, C is the coefficient, runoff coefficient, and these are all values will be the same. Okay. As the slope gradient will be given 1:1,000 like this. C is the coefficient, okay. Ignition formula is also used, Dickens formula. So by seeing all those formulas, you see that Q is directly proportional to RI and A, okay, and inversely proportional to area. These are all those things for it. Now I'm coming for the sewer appurtenances and materials. That you have done it there in the classes. Your circular sewers, rectangle, I mean, various design rectangular sewers, egg-tip type of sewers. Design of sewer depend on various parameters. As you know, in a sewer water, 99% water is there and 0.1% solid matters. Okay. Then selection size of the sewers depend on various things you have to consider it. Sewer gradient you have to consider it, right? Non-scoring velocity or maximum velocity you have to consider it. Hydraulic formulas used for design of sewer. Two commonly formulas used, like one is the discharge formula, that is continuity equation Q is equal to N to V, and V you have to take it through the Chezy's equation, and this velocity, and you can take it through the Hazen-William, that is this formula, and third one is the Manning coefficient. So this V Q is equal to N to V, the velocity you will get it from the three equations, Chezy's, Hazen-William, and the Manning formulas. While the designing of sewer is considered, these two things are important. And this is the design of sewers for the partial flow conditions. The sewer is running full or sewer is running partially full. So these typically I have shown it in this. Yeah. But we don't have time, so I'm just explaining here. Here these are the formulas, the ratios you have to calculate. Small d by d, proportionality depth ratio, proportionality area ratio, proportionality perimeter ratio, and proportionality hydraulic mean depth ratio, small r by capital R. Standard iterations are there. Here sewer material requirement of sewer materials. So to check the resistance of corrosion, resistance to abrasion, strength, durability, weight of material, various mechanical properties and hydraulic properties you have to choose. These are the material available for the sewer materials: asbestos, cement, steel, brick, plastic, cement, concrete, wooden, cast iron, stone, there. Various advantage and disadvantage by using these materials. And as I told you, design of sewer for the separate and combined system. Chassis formula is important, Manning formula is important, as in William formula and discharge formula. We have done a couple of numerical in the regular classes. Just go through that. I will share you the problems PPT. So numerical they have given here. Construction of sewer lines has to be done on various parameters. Offset line parallel to the center line is marked on the ground with the help of X at 7.5 interval. And then alignment and gradient of the sewer you have to choose. Then excavation, timbering, and dewatering of trenches. Then testing of sewer is required. As I told you, we have a water test and air test. We have gone through in a detail actually for the all types of test for detecting the leakages, or for before starting the sewer pipeline, first time inspection is required. So that also we are going for the smoke test and water test and air test. And we have two purposes we have to full. One is the if it is a old sewer pipeline, regular maintenance purpose. If you want to identify the leakages, if you want to identify the something, the sewer is clogged because of because of the sewer impurities are deposited on the bottom, or maybe some tree leaves are blocking the sewers, right? So identifying the blockages and all that, you have to identify the location first, then you can repair it. So these are the things. And then once the sewer pipeline is aligned and layout is complete, and excavation and placing the sewer line is done, and leakage proof actions done, then you have to refill the soil. You have to refill the pavement actually. For the construction of the sewer, various appurtenances are also required: manhole, drop manhole, lamp pole, street lines, catch basins, ventilating shafts, sewer outlets, inverted siphons, and grease and oil traps, flush devices, right? Yeah. Yes, and here we have Lever is actually for this definition, this calculations. So here you can check it. These formulas also how you are using it for numerical activity. How to solve the numericals. Simple numericals will come. We have solved in the classes actually. So they will not ask the whole thing. Sometimes they can ask the hydraulic mean depth tests. Sometimes they can ask the HMD also simple. Parametric ratio also P by P. So you must remind the concept only the Manning coefficient, then velocity of flow also they can ask. So some numericals there we have done it here. What of sampling methods, it is not there in these levels. Skipping. Wastewater characteristics. We have done the detailed analysis for the wastewater for the water treatment characteristics. There only wastewater characteristics also I have summarized it. I have explained there. So I'm not going for the details. There are the physical characteristics, chemical characteristics, and biological characteristics. Physical characteristics include with the physical parameters like turbidity, color, taste, odor, temperature, right? Totals already will be in a chemical. Yeah. And then chemical characteristics like COD, chemical oxygen demand, total organic components, and then nitrogen, phosphorus, chloride, sulfate, alkalinity, pH level, heavy metal components, trace elements, biochemical oxygen demand, all will come in under the chemical. Biochemical will be in the biological demand, actually. Yeah. So and then finally, biological characteristics to check the MPN number, to check the pathogens, how many bacteria are there, how many pathogens are available in the water. There are the two tests there, as we have gone in the detail in the last my second lecture for the GATE classes. So we have explained there the MPN test, right? Microbit. There are the two tests, qualitative test as well as the quantitative test. First is you have to identify whether bacteria and microbes are present in the water or not, testing it. And second is what are the percentage of bacteria and microbes are present, in the water. So MPN test we have conducted for this, right? So these are the things. Not going in the detail, just briefly I will explain. Color, order, various units, temperature, total solids, turbidity, chemical characteristics. These are chemical characteristics. Just go through the PPT and then. This is the estimation of biological chemical demand. This is the biochemical oxygen demand is the amount of dissolved oxygen needed by aerobic biological organism to biodegrade the organic matter within an incubation period of uh, 5 days or 21 days uh, at a temperature range of 20 degrees Celsius, okay, for a specified period like 5 days. So only organic matter present, how much oxygen will be dissolved, yeah, consumed by the bacteria. Give the strength of BOD, strength of series by BOD will through this BOD you can identify the strength of the series can identify based on the BOD content. Unit will be mg per liter or ppm. We have already done this. All right. There are the two demands here: carbonaceous stage, first stage, and nitrogenous stage, second stage. In the first stage, what happens? The portion of oxygen will be consumed by the bacteria, and all the carbonaceous oxygen organic matter will be consumed by the bacteria. Okay, the first 20 days. And nitrogen, the second stage demand, all the nitrogenous matter will be consumed by the bacteria. Yeah, all the ammonia, nitrates are converted into the nitrate, and nitrogenous oxygen demand generally begins after 6 days. Like this, two demand will happen. There's the testing for the biological oxygen demand, dilution, direct method, and dilution method. These formulas we have already know about it. We have already done in the GATE classes. So BOD5 will be oxygen consumed in dilution factor. Dilution factor means how much wastewater, stream wastewater quantity you are going to dilute with the fresh water. So that ratio you have to calculate, that is called as the dilution ratio. So volume of diluted sample divided by volume of undiluted sewage sample. Do initial test. And 5 days uh, and if this DO content, that is DO final, it should be reduced actually because biological bacteria will consume the oxygen. And then DO initial and DO final you will get. So first stage BOD curve, it is L naught is the oxygen equivalent of the organic matter present in seaways at beginning. LT is the oxygen equivalent of organic matter present in any time. T is the time in days. And YT is the oxygen equivalent of organic matter exerted at any time. Then you can derive this formula that I have told you. LT divided by L naught is equal to 10 to the minus KT. We just remind that LT is equal to L naught into e to the power minus KT. LT is equal to L naught into e to the minus KT. If it is in a 10, log 10, then you can go in there. And K you will get it if the K and K dash, that also we have explained in that class. K and K dash difference. 1K is for the exponential demand, exponential value. 1K, another K dash is the for the 10 log 10 values. Okay, so this K is for the log exponential value, and this K is for the 10 value. So if you want to convert 2.303, you have to divide it base rate. This is second BOD, second stage BOD curve. Carbonaceous demand will be fulfilled, and then there's the combined demand, carbonaceous matter as well as the nitrification will be taking place, and denitrification will be taking place. Yeah, they have time versus BOD curve, they have mentioned here, and then like this. This is one equation. This one numerical is given. Suppose determine ultimate BOD for a sewage having 5 days BOD at 20 degrees Celsius as 160 mg per liter. Assume deoxygenation factor content as 0.2 per day. Then you can get it like this. Use this equation and another equation. BOD5 is given. L naught you have to determine. So BOD5 is equal to L naught into 1 minus e to the power minus KT. Directly put the answers in 1 day BOD. Another example for it. Another, like if the temperature is also given here, then this equation will be used. At 3 days BOD of a sample of CVS 250 mg, what will be the 5 days BOD at 30 degrees? If temperature is given, then that equation also you have to use it. That also I have explained in the class. It is equal to K20 into theta to OT minus B. Okay, go through my previous slides. You will get it all. We have done some numerical experiments. So same way, you can solve it here also. Another example, 5 days BOD of the base you have to calculate. Ultimate carbonaceous demand you have to calculate. What would be the remaining oxygen demand after 5 days? This is the common formula for the DO initial minus DO final multiply with the dilution factor. Yeah, the dilution factor will be directly dehydrated in a P factor. Okay. So DO initial minus DO final divided by P dilution factor. Here the same you can solve this equation. So all the three ABC you can get it. Is the dilution fraction here volume of wastewater plus volume of wastewater plus volume of diluted water. Very simple examples like this questions will be coming from the BOD. On characteristic they keep asking questions. Other questions is yeah. Correct. These are the things that we have studied. Same thing that we've done it. PPT3 module. That was the last PPT that we have discussed in our regular classes also, right? The layout and construction of sewer line, setting out alignment and gradient, excavation of trenches, timbering and backfilling, testing of test, hazards. That also we have discussed in a very detailed manner, right? protective safety equipments we required. If we always avoid the main to go inside the manhole because a lot of that's happening and it is not good for the safety point of view. From the aesthetically also it doesn't look good from the humanity point of view. So we always avoid. We try to go through the machines and some technology we have to use to for detecting the leakages, right? So there are the lot of inspection and detecting the leakages. Lot of tests are there. Lot of techniques are there that we have discussed for. We are taking the ultraviolet rays is also for detecting the leakages. We are using sensors, we are using detectors nowadays. We are using various types of cameras, digital cameras, as well as we are using various types of cameras for detecting the leakages, right? And we always avoid to send the person inside the sewer lines. So anyway, if a person is required to go inside, then what are the protective instruments that he has to carry? What are the how many persons are required for it? These all these things. So traffic, wherever you want to repair the sewer pipeline, then you have to block the road actually for the particular the dimensions. You have to indicate clearly the traffic warn alert signals to provide. No smoking, open flame should be allowed, right? In that because methane will be generated in anaerobic digestions, right? There's a lot of flammable gases will be coming out. So for avoiding the accidents, sparks should be guard against whatever the instrument you are taking inside. It should be electric proof, right? Explosion proof electric lighting equipment you have to use it. Mirror for reflection of light should be used. Atmosphere testing should be done before that. We have to test the atmosphere for the noxious gases and oxygen deficiency surrounding. We need a we need a sufficient amount of oxygen inside the sewer pipeline if you are sending the person. So oxygen cylinder he has to carry, or you have to blow on the sufficient oxygen inside so person can survive easily. If it is not, then forced ventilation required should be restored by using a portable blowers. In normal atmosphere, workers may enter in the manholes and sewer with the safety harness attached with the two men available at the top. Protective safety equipment, gas mask, oxygen breathing apparatus, portable air blowers like this. These equipments are required. Portable light equipment, safety belt and inhalers. Sewer clearing equipments and devices that you have to carry. Portable pumping sets, sectional sewer rods, flexible sewer rods, sewer cleaning, bucket machines, treasures and all that. Ventilation of sewer purpose it is for continuous flow, disposal of sewer gases, and prevention of unpleasant odor. These are the objective for it. Method of ventilation: manholes with gratings, ventilating column shaft, use of mechanical devices. These are the various methods. To reduce the fall and floating materials causes clogging of the pump, and the sewage contain organic and inorganic waste causes corrosion and erosion of part of the pumps, reduce the life of the pumps. For that purpose, sewage pumping is required. Flow varies continuously, pumping operations need to be adjusted, so that's why pumping is required. Failure of pumps happens because of the flood and silt deposits at the bottom. So elements of the pumping station, grid channels are required and courts or fine skins required, some for bed for well, pumping rooms, dry wells, pump with driving engines, motor mist, all those things are required. Pipes and walls are also required. A lot of arrangement required for it. Emergency overflow, we need a standby mode pumping stations, right? Ventilation fans and blowers, flow recorders. These are the types of pump which are frequently used in sewage treatment plants. Centrifugal pumps, axial flow pumps, mixed flow pumps, radial flow pumps, and reciprocating pump. Various designs for the pumps. See, suppose there's a standby mode, two pumps are there, right? Flow rate can be divided. The cross-section view of the centrifugal pumps. There's a radial flow pumps, there's axial flow pumps, and mixed flow pumps. As I told you, methods, self-filtration methods for the disposal, right? These things in the classes we have gone through that. Why sewage effluent disposal is required? If the sewage is treated, where you can send it, you have to dispose it of somewhere, maybe through the land treatment. And there are the natural purification methods. If the sewage is not treated, suppose if it is a domestic sewage, if you want to dispose it of in the river water body, flowing water body, it will be treated with the natural purification methods. The most commonly method called as dilution process, dilution method. And once you get the sewage effluent, there's a land treatment also, land treatment techniques. That is the two methods, dilution method as well as land treatment. So there are the various things like self-purification of the rivers and the stream. We have to study oxygen sag curve, factor affecting self-purification, Streeter-Falpe equation, numerical on self-purification of rivers and streams, wastewater disposal by treatment. Wherever, when we have started, what time, you please tell me. We will stop the lecture. It should be a 2 hours recording, so we'll stop it, and tomorrow we'll continue. Okay. So you tell me where we have to stop. If it is a 2 hours recording, then we'll stop it. I think we have started 4:13 or 4:15. Pranati, you remember that? What time we have started? Right now 6:05. Okay. Then remaining portion tomorrow I will discuss in details, right? These are the natural method of wastewater disposal. Number first is by dilution. Number second is by land treatment. Some of the artificial methods like primary treatment, secondary treatment, these are all about sewage treatment plants, the primary, secondary, and tertiary units, right? So that is another thing that we'll talk later in the next class. Right now we'll talk about the natural methods of wastewater disposal. So dilution, what is dilution? Dilution is the primary method of natural disposal consisting of discharging the wastewater into the receiving water body. The sufficient DO is available in the water body to satisfy the BOD demand. This is the condition for dilution. The composition, quality, and characteristic of the sewage. If sewage is coming, there's a primary treatment and secondary treatment. This line is reserved for the sewage treatment plant. And natural methods by dilution as well as the by land treatment disposal. Sewage water, you have to send for the respective sewage treatment plant, collected sewage should be treated. Once it is treated, sometimes what will happen if secondary treatment is not required, after primary treatment directly you can send it for the disposal, this wastewater, if the sewage water is not highly polluted. So after primary treatment you can send it partially treated and send it to the river, there river and lake where the sufficient amount of dissolution is present, and then by the dilution practices it will be automatically purified. Okay. In the ocean also we can go for the land treatment, right? So if dilution water is not, if diluting water is not sufficient to supply BOD, to oxidize the entire organic matter, the nutrients of fall order, half digested floating matter, putrefying matter at the surfaces. In this case, depletion of the oxygen kills the aquatic life and danger to the public health of drinking. Modern practices, primary treatment before the effluent is disposed of by the natural methods recommended. So go for the primary treatment of the wastewater and then dispose it off of the effluent to the by natural methods. The disposal by dilution we'll study first. Is the process whereby the treated wastewater or effluent from the treatment plant is discharged either in large static water bodies, lake or sea, or in a moving water bodies, rivers and streams. The discharged wastewater or effluent is purified naturally with the course of time. It's called as the self-purification process of water. These are the conditions as I told you. The condition favoring dilution without treatment. Sewage should be fresh, no floating and suspended solid present, no toxic substances present. Water body should have a high DO. The diluting water body should have a high DO content. No, not being used for the water supply and navigation. Directly, water should not used for the drinking purpose and navigation purpose. It should be used for the should be of the same. Coming to the compared to the river or lake wherever you are going to dispose it of. Another condition is there should be a thorough mixing or diffused capacity. Water should be flowing in continuously, and there are the swift forward currents are available. So no deposition of the sewage at the side, and no industrial wastewater should mix there. So what will happen if water is flowing with the turbulence, motion, and swift forward current is happening? So what will happen? Sufficient amount of dissolved oxygen from the atmosphere will be dissolved easily, and more oxygen is there, then more dilution will be there, and the self purification will be very easier. And another thing, where the receiving water body is not a source of drinking water collection immediately to the downstream side. Essential condition for the treatment before dilution. Wastewater discharge is detrimental to aquatic life, then you have to treat that and provide natural treatment first, but not under primary treatment and dispose it of. You remove these heavy contaminants and then make it normal and then send for the dilution. Wastewater contains suppose industrial wastewater, then toxic substances or industrial effluent is quite warm, then you have to treat it and then you have to dispose it off for the landfill. Volume of diluting water is quite insufficient. Receiving water is used for inland navigation. Receiving water is a source of drinking water. Then treatment is essential. Artificial primary treatment. Stagnant water, stale water case. Effluent is not likely to be dispersed easily due to the tides, winds, and cross currents. And this is the standard of dilution. Tomorrow lectures will be very important. Tomorrow I will talk whatever you have not studied. I will talk in detail about the sewage treatment plant, the secondary biological treatments, and primary biological treatment, mainly design part. And most of the questions will be coming on that only. Okay, this is kind of background only. They may ask or they will not ask. And this natural purification they will ask question. Dilution they will ask definitely questions. On dilution and land treatment they ask questions on this. Dilution factor, as I told you, the ratio of quantity of receiving water to that of the wastewater or effluent discharge is called dilution. These are the dilution factor that you have to consider it. Above 500, no treatment is required. Between 300 to 500, primary treatment plus plant sedimentation is required. If you are getting dilution factor 150 to 300, then sedimentation, skinning, and chemical precipitation is required. Effluent does not contain more than 50 suspended, more than 50 ppm suspended solids, right? And less than 150, wastewater should be treated thoroughly. Effluent does not contain more than 30 ppm suspended solids. 5 days VOD at 8.3 degree does not exceed 20 ppm. So these are the conditions for various dilution factors. So that you can do it in laboratory, and then based on this you can finalize which treatment is required for it. Type of receiving waters for the dilution: perennial rivers, streams, lakes, oceans, seas, estuaries, wide lower tidal part of the rivers, creeks in the form of an inlet on sea coast. Capacity of self-purification, because perennial river water is in a continuous motion, natural streams balance between plants and animal life. Dilution factor in summers may be low. High temperature of water, if temperature is high, solubility will be low. And of course, the dissolved oxygen, high temperature, dissolved oxygen will be lesser. Okay. So low solubility of oxygen will be happening, means at a high temperature, there is a low dissolved oxygen present in the water. Lakes, examination of various factors. You have to examine size, sea, volume of fresh water flowing into or before deciding the self-purification capacity. Ocean has abundant water of dilution factor, because dilution factor is limited for the ocean. Ocean water is having more than 20% less than river or lakes water. Turbid water due to the dissolved impurities. Penetration of sun rays are less. So dilution in sea results anaerobic conditions leading to the formation of sludge banks and emission of fall odors. Okay. How the self-purification occurs of the natural streams? Have a sufficient amount of oxidation materials to ammonia, right? And this dissolution of water utilized. So deficiency of dissolved oxygen is created. Excess organic matter is stabilized. The normal cycle will be established in a process known as self-purification, wherein the oxygen is replenished by its reaeration by winds. Again, the amount of oxygen will be supplied from the atmosphere. Also, the stable byproduct of oxidation are utilized by plants and algae to produce carbohydrates and oxygen. Actions involved in self-purification are self-purification of physical, chemical, and biological in nature. Affecting factor of self-purification of streams are dilution, dispersion due to currents, sedimentation, oxidation, reduction, temperature, and sunlight. These are the affecting factor of self-purification. So, zones of pollution in the stream, there are the four zones: zone of degradation, zone of active decomposition, zone of recovery, and clear water zone. Self-purification, how process will occur: the wastewater is discharged into the river or the stream. The BOD of the mix increases initially, and DO levels start falling. As river water travels further, BOD gradually reduces and DO increases and reaches its saturation level. Thus, river gets purified on its own. This phenomenon is known as self-purification of the stream. You see there, this is the zones. This is the graph between on x-axis. There are the zones. Time is given with respect to time and days, and here the dissolved oxygen consumed level is given on y-axis. So the clear water zones, sufficient amount of dissolved oxygen there, aquatic life is fresh. There is no discharge of sewage water here. So this is a fresh water body, river. Now at that point, fresh the sewage water, partially treated sewage water is discharged in that. So once you discharge that, immediately bacteria present in a wastewater start consuming the dissolved oxygen present in the water, and then the amount of dissolved oxygen start reducing, and this stage is called as decomposition zone. This is the saturation level. Top will be the saturated level of DO, where sufficient amount of DO present, and it will reach up to the least limit where the excess amount of DO will be consumed by the bacteria, and this zone will become almost anaerobic, where the amount of oxygen will be nil or very partially available. This zone is called as septic zones. And then finally, after that, what will happen? Because of the re-aeration, because of the diffusion, because of the water is having a forward eddy currents, and then again the atmospheric oxygen, extra atmospheric oxygen will be supplied from the atmosphere. Again, the oxygen level will start increasing. It will reach to the recovery zone, where some of the plants, some of the aquatic life is doesn't reappear. After that, water will reach to the natural saturated DO level, and finally water is treated. And there, this water will again self-purify, or it will become clear. The cycle will be repeated like this. So actions involved in self-purification of the streams, in all the whole process, what is happening? Dilution is happening, dispersion is happening, sedimentation is happening, oxidation and reduction chemical reactions are happening, and then of course it's a temperature based in sunlight, so that is also important. Yeah. So while the wastewater is mixed with the river water, the concentration C of the resulting mixture is given by using this equation. Concentration of the sewage CS, flow rate of the sewage CR, sewage, and flow rate of the river QR. So this is the mixing equation. That equation we used to use it. So C is the concentration of a mixing, or concentration after mixing, right? So C is the mixture concentration. What will the mixture? So this will be the equation that we are using it. We have done a numerical on this. Okay. Dispersion due to currents and all that. Sedimentation is physical sedimentation. Temperature, as you know, temperature increases, DO decreases. And pollutions and tomorrow I'll continue these all those things. After that, I will directly move for the sewage treatment plants. These things I will continue tomorrow. Okay. Yeah. So thanks for the class. We'll wind up the session today. I think our time is up. So yeah, it's recorded. I think done. So next class today, tomorrow you attend the class. I will be talking about the primary and secondary treatments, which is very important. If we remain time, then we'll move for the air pollution and solid waste management also. Okay. Thank you.